What? Sorry.
No. Do the video now? No. Well, these are only to be viewed by us anyway. So
we can start the video. We shall sing Kariyama
Woodson. What? Carry on, my wayward son. Understood. Yes. Yeah. Now, oddly enough, there are songs that when I hear them, I'm like, I need to play Guitar Hero right now. Like I just want to get on Guitar Hero World Tour and just get drumming. I just super want to get in the mood for that. But sadly, my dog chewed the cable that goes from the drum set to the drum pedal. And now what do I do? I don't know. I've got giant plastic garbage now lying around that I can't do anything with. So anyways, welcome. So let's look at last night's homework. Question 21. Divide using synthetic division and write your answer in the form dividend equals quotient times divisor plus remainder. And then answer this additional question, which is the binomial a factor of the polynomial? Right? So looking at question 21, let's write this in synthetic division form. So here's 21. So negative 2 would go in the box, right? When I have it written as a factor, this will be the opposite of that, okay? But if I was calculating the value of a polynomial, it would have been the same as the little a value there. So f of negative 2, it stays the same. If it's x minus a, then this is positive a, so these are opposite in that case. So, let's see, does this need any placeholders? 6, 9, negative 6, dose, it doesn't look like it does. And let's synthetically divide. So add, and then multiply, add, more influential number keeps the sign, right? So make sure you know how to do that. That's a positive 6. Oh, adds to be 0. Ooh. 0. It looked like it was going to be so close to having a remainder of 0. But sadly, no. So let's write our answer as the dividend, all right, the thing I was dividing by, 6x cubed plus 9x squared minus 6x plus 2. Is that equal to the quotient, which is this part right here, right? This is going to be 1 degree less than the dividend. So that would be 6x squared minus 3x. And there's no constant term, so that's kind of like a plus 0 or something like that. Quotient times divisor. My divisor was the x plus 2. And then I will add on the remainder. Oh, I was going to write r there, so 2. So this would be our answer. And let's see, verifying, cha-ching. Now, to answer that last question, it says, is the binomial a factor of the polynomial? And based off of this, here I've written this expression as the product of 2 expressions, but then I've got like this little plus a little bit of change over here. If this wasn't here, then I would have had it written as the product of 2 expressions, and it would have been factored, where one of the factors was the divisor. However, because I have this little plus remainder, it doesn't work out, so no, x plus 2 is not a factor. So that's a shame, but that's okay. All right. And then if I asked a follow-up question, just to relate it to our synthetic substitution, if I asked you what is f of negative 2, what would you tell me? Hello, hello. Welcome, welcome. Let's see. Do I have attendance still logged in? Yeah. Oh, you're already marked. Okay, thank you. Thank you. Now, yeah, we got new seats. Does anyone remember where it sits?
There, somewhere.
Yeah, I think you're next to Ant. Or maybe one... I don't remember.
No, because Colin...
There we go. It all works out. So, welcome back. Welcome back. So let's see, for problem 21, if I asked us what is f of negative 2, what would you tell me? F of -2, library crew in the back. Is 2, right? It's just equal to the remainder. And that was kind of the cool property that we learned yesterday, the remainder theorem, that the remainder is equal to f of a, all right? Where instead of doing direct substitution and plugging 2 in for all of the x's in this function and finding out what it gives me, I can just do synthetic substitution and steal the remainder. So other questions on the homework? Anything? 23. Sure. How did you guys do on the last batch? Okay. You got them all? Who said all right? Wrong?
Right.
Oh, that's good. That's good stuff. Let's see. So I'll just recopy that there. So here's 23. So we'll do the same setup. I'm going to cruise through this one a little quicker. So the opposite. Yeah, where's my? So I've got 1, and let's see. I've got 4. Oh, 0, -2, 1, 1. So could someone explain to me why that 0 is there? What does that 0 represent? For which term? The x to the third term was missing, right? So we didn't know where was x to the third, so we had to represent it anyway, making sure that it was marked absent, right? So let's see, let's add multiply. So bring down the 4, multiply by 1, add, multiply, add, multiply, add, wait a minute. I think I've...
No, you're right.
Okay, I was worried I was multiplying by 2's for a minute there, and then I was confused. That would do it. And then add. So let's see. So my answer written in that quotient, nope, sorry, dividend, is equal to the quotient. This is my quotient right here, right? So that is 4x cubed plus, that kind of looks like a 9, but pretend it isn't. Right, so here's my quotient multiplied by my divisor, x minus 1, and then plus my remainder, and here's my remainder, so plus 4. So is x minus 1 a factor? No, because I can't write it as x minus 1 just times something, because I get this little bit of scrap left over. So x minus 1 is not a factor. And then, what else could you tell me if I was trying to figure out a value of this function by plugging in blah, 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 substitution? What else could you tell me about this problem if we were to expand it? Something else, you know. I'm not asking the question in a very good way, but. Yeah. Right. If I was considering what information this told me based off of direct, synthetic substitution, I would know that f of 1 is equal to positive 4. Right? Where if I plugged this in for x into the original problem, the output would be 4. Right? So there's that kind of interesting relationship there. Okay? So are we all good on that then? Let me just save this. Saving. There we go. So let's take out our notes, or you can put your homework in the folder if you'd like. And let's see, so 489. It's going to be part 1 technically, but...
I should tell you now, I'm going to be blind for like the next 2 weeks.
Blind?
I don't have any contact. I can't wear contacts. I have
okay, not completely blind?
More like even sitting here, I can't see.
All right. What do you have for ideas or suggestions?
I have no idea. I'll probably rewatch them on my computer to get a closer view of everything. I can kind of see some stuff, but it's all very fuzzy.
Oh, wow.
I just thought
Okay.
I'd let you know in advance. So
Yeah.
It's not me taking bad notes. It's my eyesight. So
Man. Huh.
I can.
Yeah, you can keep it, actually.
They tell me that I can't wear them and I have to take these eye drops. So
Wow, that's crazy.
and my glasses don't come in for 2 weeks. So.
Huh.
I'm a little SOL.
Yeah. I always thought it'd be interesting if you could get a touchscreen device that not only represented where the image was, but you could have per pixel depth, so you could almost have like a braille image that's dynamic. Yeah. That'd be pretty cool. But now, oh no, I just broadcast that idea on the internet. Someone's going to steal it from me. Oh well. I don't think anyone's ever going to watch this video other than students of myself, anyway. Let's see, so...
Well, until like the second half of the day it is.
So welcome, ladies and gentlemen. Today we are talking about the Factor Theorem. The Factor Theorem. Actually, I wish I saved a snapshot from that previous thing. But let's start off with a consider. Consider the following. I'm just going to pretend I just did a whole synthetic division problem and I ended up with this as an answer. X to the fourth plus x cubed minus 13x squared minus 25x minus 12. Right, so this would have been my dividend, and I found that it was equal to x cubed plus 5x squared plus 7x. Am I going to run out of room? I hope not. Plus 3, so there's my quotient, and my divisor was x minus 4, and my remainder was 0. Oh, absolutely. Don't worry about it. So we just discussed the fact that if I had this with a remainder of 0, that notice that this expression, my dividend, has been written as the product of two expressions. So these two expressions are factors of the original problem, okay? Because this remainder was 0, right? Since it had no effect. So that told us that our divisor is a factor. So in kind of pulling those ideas together, I'm going to just snapshot this right out of the book. So this is called the Factor Theorem. And it kind of just puts a whole bunch of stuff that we've been saying all along, buttons it all up into a nice little theorem for us. So it says that the binomial x minus a is a factor of the polynomial f of x if and only if f of a equals 0. So, to put this into words, it's basically saying that this is a factor of the polynomial if my remainder is 0, right? Which is kind of what I said there. But then we took it one step further. If f of a is 0, if when I plug the value of a into the function, I get 0 as an output, all right? Which, graphically speaking, if I plug in an x value and get 0 as an output, what kind of point is that? What has 0 as a y coordinate? What kind of points have that?
Y-intercept?
No? 0 as the y coordinate would be a point on, or where? Well, you kind of gave me a horizontal gesture.
Well, yeah, but it's right in
Well, 0, 0 is at the origin of the graph.
An X-intercept?
So an X-intercept could have any x coordinate, and the y coordinate would be 0. Right, so it turns out that a I guess, additional fact that I'll tell you. I probably am not supposed to tell you yet. But A is an X-intercept as well. Okay? So this is just kind of saying facts that, pulling things together that we already knew. So if the divisor is a factor, what I'm left with here, the quotient has an interesting relationship to the original polynomial. All right? Where this x minus 4 is telling me that one of the x-intercepts is positive 4. All right? Right? That's telling me that f of x is 4. And it turns out that this... Well, actually, let me ask this question first. Let's pull all, as many of our concepts together as we can. If I had the polynomial f of x equals this x to the 4th thing, how many x-intercepts could it have? How many x-intercepts could this have? It could have as many as 4, right? Right, so this has 4 x-intercepts. How many x-intercepts does this x to the 1st minus 4 have? If this was its own polynomial, if I had f of x equals x to the 1st minus 4. That'd be 1. And then how many would this polynomial have? 3. And it turns out that the 3 x-intercepts that this polynomial has are the other 3 x-intercepts that this one has. All right, so this has 3 of this polynomial's x-intercepts, and this has the other one that we already know, which we know now that in that example that f of 4 equals 0 is what we would be able to say, right, from that expression. So f of 4 equals 0, or we have the point 4 comma 0, or an x-intercept is 4, right? So all that information we could pull from that. But that's what's interesting is that this other polynomial, my quotient, has the other 3 x-intercepts. And it turns out what we'll call that polynomial is, this is referred to as a depressed polynomial. Okay? So that is a depressed polynomial. And if I could find another factor of the depressed polynomial, I could actually end up finding eventually those other 3 x-intercepts if I could break that down and factor it all of the way. Actually, let me start up my geometry sketchpad. I think I've got a decent little file that demonstrates the relationship between these. But as that's starting up, we'll continue with this. Let's see, open. Where's my depressed polynomial file? Nope, that's not what I meant to do. Here we are. File opened. Let's see. I made one of these last quarter. Let's see, Math 3. Where's my depressed polynomial file? Here we are. Aha. Okay. So this is kind of a crazy looking visual representation of this. Let me full screen this. Okay. And I might make this darker. What's a good color for that? Maybe a blue or something. Or maybe just a dark green. There we are. Okay. So what I have here, this purple polynomial, is this 4th degree. Okay. Actually, I wonder if no, I don't have sliders that go all the way up to 13 or 25 like the one I had. But so this purple polynomial is like my original one, and it's got 4 x-intercepts here. All right, and let's say I knew what this x-intercept was. All right, this point k is pretty much -2 comma 0. All right, is what's going on there. So if I synthetically divided by x plus 2, or x minus the opposite of that point k, right? So x minus a negative 2 is x plus 2. I would end up with a depressed polynomial, all right? And that depressed polynomial is represented by this green function here. And notice that it's an entirely different function. It's it's one less degree than the original, right? The original was a 4th degree. This depressed polynomial is the classic little squiggle of a cubic function, so it's a 3rd degree. And notice the only thing that I'm interested in about this is what it has in common with my original, and it happens to cross at the same x-intercepts as the original, the ones that I didn't yet know. And it turns out, no matter how I arrange it, I'll get the depressed polynomial. So in this case, my original only has 2 roots, and the depressed one will give me the second one that I didn't yet know, right? I'm assuming I already knew what the k one was, right? So no matter how I manipulate this, the depressed polynomial will always pass through the additional x-intercepts that I didn't know about. Let's see. Right, so I think that this is kind of like a crazy relationship here. Let's see what happens if I get some positive ones going here. Oh, that's a 3rd degree there, isn't it? Yeah, so check this out. So if I know one of my x-intercepts, then I know one of the factors, right? So if this is the point negative 0.48, then that means one of the factors would be x plus 0.48, okay? And if I was to divide that out, it would give me a depressed polynomial that would contain the other 3 factors. All right, so depressed, don't think of it as like a sad polynomial. It's depressed as in like it's reduced, like pushed down, depressed sort of thing, like, you know, something less than what the original had, right? Something like that. So you can see that it ends up having that relationship. And oddly enough, if I could then find one of the x-intercepts of the depressed polynomial, I could find another polynomial that is even more depressed than that one. And that would contain the other 2 x-intercepts that one didn't have. And then I could find one of those and then find an even more depressed polynomial which would contain the last one. So you can actually end up like kind of going all out here. Actually, I wonder if... nope, that's not what I wanted to do. Let's graph a new function. Let's see if I can do this. What if I divide function g of x? I think that's what I want. And I divide by a new expression which would be x minus, and let's just say this point L, or something like that. All right, so if I take my depressed polynomial and divide by another of its x-intercept factors, theoretically, check this out. What do you know? I get a 3rd level of depressed polynomial, and it happens to pass through the other 2 points that I don't yet know. Let's see, do I remember how to increase that? There we go. So let me make that thicker and whatnot. And we'll give that a color blue. Right? So, so notice that this blue polynomial is 1 degree less than the original depressed polynomial, and it contains the other 2 points that I didn't originally know. Right? So it's just this interesting relationship going on here, and so that's visually what's taking place. And today what we're going to do is algebraically find these things using synthetic division. All right, is what we'll do. But I just want you to kind of understand, like, these depressed polynomials have nothing in common with the original graph other than the fact that their equation is a factor of the original and that they happen to have missing x-intercepts that we don't originally know about. Okay? So that's kind of the big idea there. So let's show you what we'll use this with. Let's see. So let's do an example. Let's see. I think I've got a good one here. Yeah. So let's say if f of x equals x cubed plus 5x squared minus 12x minus 36. And let's say I told you that one of the factors, that's a semicolon there, was x minus 3. All right. Eventually we'll have techniques of guessing what an initial x-intercept will be. At this point in this chapter, they'll give you kind of your seed factor. They'll give you a starting point that you can synthetically divide to figure out if it's factorable, and then to get depressed polynomials and go from there. So they'll give you a starting one, but eventually we'll have some strategies to find that, to begin with. So the directions for this would be something like, let's see, actually let me steal the directions right from what our homework will be. It'll say, given a polynomial and one of its factors, let's see, I might as well make sure that we're ready for our homework tonight, right? So yeah, given a polynomial and one of its factors, find the remaining factors of the polynomial. Yeah, I'll just throw that right there. Right, so I've got a polynomial, I've got one of its factors, and now I want to find the remaining factors, okay? So in order to do that, what I'm going to do, if I know this is a factor, what sort of remainder do I expect to get if I divide that into the bigger one?
0.
I'm expecting to get 0, right? I was just told that this was a factor, so I know that the remainder is going to be 0. And I also know that f of 3 is going to equal what?
No, 3.
What would f of 3 be if I plug 3 in here for all the x's? If I told you this is a factor, we know the remainder is 0, so therefore f of 3, you're right, would be 0. Okay? So I just want to kind of like piece some of that together. And if f of 3 equals 0, then what point does this represent? That's the point 3 comma 0. And that would be one of my x-intercepts. Okay? So let's synthetically divide this. Let's do this. So if I'm synthetically dividing, I'm putting 3 into, 1, 5, negative 12, negative 36. Draw my line. And so I'm expecting, unless this book was lying to us, that my remainder is going to be 0. Right? If it's not, I would be like, uh-oh, I do not have a factor, and I also don't have an x-intercept here. And I'd have to keep looking. So we'll add, bring down the 1, multiply, 3 times 1 is 3, add is 8, multiply, 24, add, I get 12, multiply, I get positive 36, and add, I get 0. So that 0 confirms to me by the factor theorem, right, that x minus 3 is a factor of the original polynomial. Okay? It also tells us that this is an x-intercept, right? So it verified that for us. And now I also have a depressed polynomial. I'm going to write this in a different color. My depressed polynomial I'll call g of x, and that will be the quotient. All right, so x squared plus 8x plus 12 is my depressed polynomial. I'll throw the name up above it there too. So I'll say this is the depressed one. And I know that the x-intercepts that this depressed polynomial has are the other 2 x-intercepts, because I was expecting a total of 3. I know 1. And I know that this depressed polynomial has 2, right? So 1 plus 2 is 3, right? So I'm verifying just kind of that works out. So there's my depressed polynomial. So if I can find the x-intercepts of this, I will then find the other 2 x-intercepts of that. Or if I find the factors of this, I know that those will also be factors of the original. Okay, so it's just kind of an interesting relationship between that and a depressed polynomial. So I've got some strategies now. I could try synthetically dividing this by a whole bunch of different numbers, but I don't have any good strategies of picking those just yet. But at this point, x squared, we actually know how to factor x squared things if they are factorable. How do I factor that? Does anyone get an idea?
AC method?
We could AC method it. However, even better, because the coefficient of the leading term is 1, you can even do the shorter method. But you wouldn't be wrong for using AC. It'd just be a little bit more work. So find the factors of 12 that add to be 8, right? So 1 and 12, 2 and 6, 3 and 4. So 2 and 6 add to be 8. So I get g of x is equal to x with a 2 and x with a 6. And what are the signs of these going to be? Plus, plus. And if those are factors of g of x, then that tells me that f of negative 2 is 0. Sorry, wait. Yes, okay. And that also tells me that f of negative 6 is 0, right? According to the factor theorem. If these are factors, then that means this must be true. That's what the factor theorem told us. And what that if and only if told us up here, if and only if, is a logic statement. It's kind of bizarre. It feels weird. But it means that it's true either direction you read that sentence. So that means if I know f of a is 0, then x minus a is a factor of the polynomial. And then I could also start here. If x minus a is a factor of the polynomial, then f of a equals 0. So it's true both ways, logically. All right. I believe biconditional statement is what that can be referred to as. So what are these x-intercepts then, if I want to write these as points? So that would be what, comma, what, and what, comma, what. Right, negative 2, 0, and negative 6, 0. So my x-intercepts for all of these are those points, okay? And eventually what we'll do is, right, back in the day when we were graphing parabolas, remember we'd start out with a few significant points. With parabolas, we were able to find the vertex, we were able to find the x-intercepts, we were able to find the y-intercept, and then once we had that information, we were able to graph it. If I can find the x-intercepts of this, I might have a general idea of what this graph looks like. And then we could pull in other information. You won't be doing this tonight, but I could pull in other information from this polynomial. So for instance, I know, okay, it's a third degree with a positive leading coefficient, so it's shaped like this. I know what the end behavior is. I know that the y-intercept is at negative 36, right? So like somewhere way down here is a y-intercept negative 36. And now I also happen to know that it's got 3 x-intercepts, and I just found them. Let's see, which actually 2 of them were negative, 1 was positive. So, but I'd be able to get a general idea of that graph from that. Now, unfortunately, we don't have a good strategy for finding those local extrema. In the case of a parabola, the vertex was kind of in the middle of your 2 x-intercepts, right? It landed right on your axis of symmetry. But in the case of this, say I had these as 2 x-intercepts, this point right here is not in the middle of those 2 for most of these polynomial functions. So it's actually a little bit more work in order to find those points. We probably won't be able to in this course. We might be able to estimate them, okay, but we won't be able to find them. It actually will be a calculus question that you'll be able to do that later, where we'll end up finding the slope of the curve, and we'll be able to figure out when the slope is 0, right, when it's up to the hill, kind of like going over a roller coaster. Right here it's steep, steep, less steep, less steep, less steep, and then it flattens out, and there's one moment where the slope is 0, and then it starts going downhill, 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 and then the slope is 0 right there, and then it goes uphill. There's a calculus way of figuring out the slope of a curve at any point, and we'll just set that equal to 0 and solve, and that's how you could end up finding those. But right now we won't be able to find those, whereas in a parabola we do know how to find the vertex pretty easily. So let's see. So I just want to point out that another way I could write this, I could say that f of x is then factored to be, what was it, x minus 3? Yeah. times x plus 2 times x plus 6. Right? So I can represent f of x as the factors of this, this, and this. All right? So this is true. So, so there's kind of a lot of moving parts to this process, and that's why I'm just trying to connect as many dots as I can for us, just so that you can see the relationship between the depressed polynomial and the original. They have the same x-intercepts, that the factors of the depressed polynomial will also be factors of the original, right? There's all sorts of kind of things going on, and then that the depressed polynomial contains the x-intercepts that the original one has as well. So all sorts of good stuff coming from this. So let's try, I think we might just do one more example. This one's starting from a graph. So let's see, find the factors. And let's get a graph. I could steal a graph from the book, or I could actually, I don't know if I can land one in Geometry Sketchpad quick enough. Let's see, I'm going to delete that one here. I want to get one that actually has nice factors. We'll do an x to the third function. And yeah, actually that's a real nice one right there. So I'm going to snapshot this graph. Let's see. So you guys probably won't be able to have as nice of a representation of this. But you could draw a quick squiggle. It looks like it passes through at -1/2, at 0, and at +1. And I'll write down the equation of this. This is, we'll call this function f of x equals, this is clearly a negative cubic, right? Because the end behavior was flipped, right? This cactus was all like that. And let's see, what was the original function? It would be -4 x cubed plus 2x squared plus 2x, and I end up having my constant equaling 0. So I could write that plus 0 if you want, which is verified by the fact that, notice, our y-intercept is 0, right? So what we'll be doing is, since I can't really get started until I know one of the factors, this is another type of problem your book will give you tonight, where they'll give you a polynomial and then have its graph represented, and then you'll have to kind of guess what one of the factors will be based on the graph. All right? So I'll show you how we could do that. So based on this graph, I see that this has an x-intercept at 1, 0. Or I'm pretty sure it is. All right? In this case, I'm certain because I just saw it a moment ago. But so based off of that x-intercept, you pick one of the points that it happens to cross through. I could have picked 0 here, 0, 0. But we're just going to do the 1, 0. So if 1, 0 is an x-intercept, then that means, what information does that give us? That tells me that f of 1 equals 0, right? And then according to the factor theorem, what does that tell us? Any ideas, anybody? That x minus 1 is a factor, right? So if I happen to pick this point here, this -1/2, I would say, okay, so that's the point -0.50. That means that f of -0.5 equals 0, and that would mean x minus -0.5 is a factor, or x plus 0.5, right, where it would just opposite the sign there. So, okay, so now I've got my starting point. So I'm going to synthetically divide this guy by this factor. All right, so it's given me my seed value, my seed money that I can get started with and start finding these other x-intercepts with. Narrow it down. So let's see. So for synthetic division, what's going in the little corner box?
1.
In this corner, weighing in at 1 pound. 1. And then we've got my original polynomial. I've got -4 plus, oh, I don't need the plus 2. 2, 2, and then 0. Right? I've got the placeholder for the constant term. So let's bring down the -4. We'll multiply, add, and multiply, and add, and multiply, and add. So, what information can you guys tell me about this? Was I right about x minus 1 being a factor? How do we know? The remainder is 0. So, okay, so that's good news. Also, I verified that f of 1 equals 0, right? Because when I plugged in 1 synthetically, synthetic substitution told me that I did get 0 back. And could someone tell me what the depressed polynomial was?
-4x squared minus 2x.
-4x squared minus 2x. And I could have the plus 0 there, but we don't need it. So here is now a depressed polynomial. All right. Now, let me ask this question. More challenging one. Which two x-intercepts does this depressed polynomial pass through on my graph? Which two ones does it share? No. M is the one that we'd started with. So K and L. So, and this is an upside down parabola. So our depressed polynomial is probably something like this. All right, where it probably is an upside down parabola. It's probably way narrow because it's a -4, so it's a steep parabola. But the depressed polynomial will pass through the other x-intercepts that you didn't start with. All right. And if I had 3 other x-intercepts, then it would somehow swing around and hit all 3. All right. If I had 7 other x-intercepts, it would just be some crazy polynomial that hit all 7. Right. So, and what's interesting is if I started with k, say I started on this one, then my depressed polynomial would have been something that passed through the other 2. All right. So it all depends on which ones we start with. Okay. So here's my depressed polynomial. Let's find the other factors and find the other x-intercepts. So how could I do that? How can I factor this?
Divide each by -4.
To factor the expression -4x squared minus 2x, not really. If it was set equal to 0, you could. Like if I was solving for this x, but in this case, it wouldn't. Now you could consider the AC method, but the value of my C is 0. What's another type of factoring I could use? Which is GCF, yeah. I can, let's see, I guess I need another color here. I can swipe out the GCF from each of these terms. The only reason I'm doing that is because they both happen to have an x in it. If I had a constant here, I wouldn't use the GCF ever. All right, but in this case, it happens to work out. So what is the greatest common factor that I could steal out of this?
-2x.
-2x. So I'm going to get g of x is equal to -2x times what? Positive 2x plus 1. And that is actually completely factored. So if these are factors of this polynomial, translating this to x-intercepts might be a little bit trickier. But how did we find x-intercepts for a parabola back in the day? What did we do? We factored it, and then what did we do? Does anyone remember? Yeah, we set it to 0, right? Like we mentioned earlier, that X-intercepts will have Y coordinates that are 0. So if I plug 0 in for this and solve for X, that will tell me the X values that happen to have 0 as their Y-intercept. So if I wanted to solve these, I could set each of these equal to 0 and solve. And if I solve, this one solves rather easily. I get X equals 0. And this one, I get 2X equals -1, and X equals -1/2. Right, if I'd subtracted 1 from both sides and then div2'd it on both sides. So it turns out that my other X-intercepts so my X-ints are the following. I have the original one I found, and then I've got these two. All right. And if I wanted to write my original polynomial, let's see, I think I call it f of x instead of p of x. It would be all of my factors put together. So -2x times 2x plus 1 times, and then what was my original? X minus 1, right? It was a factor. So here's the factored version of a cubic polynomial. And up to this point, we haven't known how to factor a third-degree function. All right? So this is actually kind of one of the only ways we can figure that out, at least in the world of Algebra 2 or Math 3, whichever you're thinking about it as. And notice that my X-intercepts, I set 0 and -1/2, and notice 0 and -1/2 are in fact where those cross. And if I actually wanted to graph my depressed polynomial, I think I can graph this again. Bam. Oh, wait a minute. What? Oh, the issue here is that this is the depressed polynomial where I started with k as the point that I knew. So notice if I picked k, the depressed polynomial would have been that. Let's see, I think I can actually switch this. Let's see, we started with the 1. Yeah, so that's what our depressed polynomial would have looked like, something like that. Interesting. So that's kind of the idea behind this. This is definitely a widely conceptual lesson, right? I don't just have necessarily like a formula for you to do or a process, but it's kind of understanding all of these moving parts and relationships between all of these. Unfortunately, this whole chapter will be a lot on that idea of all of the relationships between these graphs, and I technically showed you way more than you need for just this one section, but I just kind of want to keep hitting home all of these relationships over and over, so that way we'll be really, really good at it. All right, so actually, let's see if I can just find a way to verbally summarize the process. So we find a factor, we divide by that factor, it gives us a depressed polynomial. If I can factor that, these two factors will also have been factors of my original. I just said the word factor like 8 times there. And then I can set those equal to 0 and also find all of my X-intercepts, and the world is a beautiful place, right? So, all right, so let's take a break, and we'll do some classwork in a moment when we come back. So 2 minutes.